Yep, looks all good from here.
Okay. So yeah, as implied, my talk is about demystifying those nasty little security certs that make mTLS work. Let's see if there we go. So why this talk should matter to you? Well, a few days ago, our friends at Microsoft had a 3-hour outage due to certificates not being rotated correctly. And so Teams was down, and I'm sure there were a lot of internal processes that led to that being a 3-hour outage. But it also shows that this can happen to anybody, even corporations that make software to help you manage certificates. Another reason why this talk might be valid is a recent CVE that was released for Nomad, where there was actually a privilege escalation issue due to incorrect certificate validation. And we'll actually go look at the code that fixed this CVE towards the end of the talk. And funny enough, when I came across that CVE, we also saw that this very similar issue also existed in Kubernetes a few years ago. So it's also kind of interesting to see that history kind of repeats itself with us not understanding how certificates work and us not understanding how to write code that deals with certificates or write test code that deals with certificates. And so it's still a fairly complex issue. And so, yeah, that's why I've started to make this talk, is because apparently in 2020, it's still hard to do certificates. We keep repeating the same errors. And my hypothesis is that it all starts with education and a foundation in the basics. So the goal of this talk and then the workshop that I should be building out here very soon is that everybody should have a way to get started with learning how certificates work, learning how to use them in software systems you love, and then actually learning how to use them in code that you write so that, one, you can go to the tools that you love and validate that they actually do what they claim to do, and two, so that if you need to write tools that actually use mTLS, you have the capability to do that, and there should be no like walled gardens or anything like that. So the agenda for today is going to be heavily focused around first principles. So we're going to spend a lot of time looking at what actually makes up a certificate. We'll look at some tools that can be used to make certificates. The next step will be hands-on practice. Typically, if this was in a workshop-styled environment, we would actually get on our laptops and do demos and work together, but that's not really what we're doing here today. So I'll give you some links on places to start to go learn. Again, you'll be able to come back to the workshop that I'm putting together at some point, but today that website's fairly blank. And then finally, we'll actually go over some of the code that's in Consul and Nomad and take a look at how they actually enforce the contracts that they claim with how they use mTLS under the hood. So when people get started learning certificates, I often find, including myself, getting bombarded with all these words, right? So is there a difference between an SSL certificate and a TLS certificate? Maybe it should be called an HTTPS certificate. Or sometimes you'll even see in the code this really weird number of X509v3. And today, if there's anything I can teach you, it's that all of these things don't exist except for X509v3 certificates. At the end of the day, all of these cryptographic protocols actually use this standard of X509v3. And that certificate format is actually defined in an RFC. So RFC 5280 clearly, believe it or not, clearly lays out the intent of what this certificate is, what is the actual data structure, and how that data structure can then be used to certify things. So we're going to briefly go over some defined terms. You're going to get really bored, and then we'll actually go through a certificate for ourselves and see how things work. So the basic fields for a certificate are a version number. So the people who created this said, hey, we might need to actually version the concept of what this certificate is. So currently we're on V3 of the certificate versioning. The next thing is a serial number. So just like a driver's license or a passport, the idea that a certificate would have a number associated with it, and that number would be unique against any of the, or against the person who created the certificate. So what's important to know is that that serial number isn't unique globally. It's just unique to the authority that made the certificate. The next little bit gets a little gnarly. So the signature algorithm, that basically tells us what cryptographic algorithm we're going to use or should be used when using this certificate with any of the instructions that we're trying to do with it. The issuer, so just like a driver's license or a passport, this tells you, hey, so I see that you presented me with a certificate, but who actually gave you that certificate, and that'll determine whether or not I trust that person or not. And then the next piece of it is validity. So just like your milk in the fridge or your driver's license or passport or any kind of ID, there's a certain amount of time that we want to trust that certificate. And ultimately that's governed by how long we have the ability to actually go ask the issuer, what do they know about this certificate? So this is what determines whether or not a certificate is expired or not. The next step is the subject. So this is actually all of the data that contains who you are when you're presenting the certificate. So you could think of like the subject as like me, Alan Sugar. When I present the driver's license to you, the subject is me, but the issuer might be the state of Texas or the state of Washington. Or similarly with passports, the subject of the passport is me, but the issuer is the origin country of which you are possessing that passport from. The next bit is subject public key info. So again, these certificates all revolve themselves around the ability to do encryption and certification of the integrity of data. So this key info tells you how that kind of works. And then finally, the extensions. So the people who created this said, okay, cool. We have this kind of generic way of setting up a framework for certificates, but obviously these certificates might have many, many, many different use cases. We should make it generic enough that these extensions could provide additional pieces of data that would allow these certificates to have additional use cases. And so not all of the extensions are documented in the RFC, but a lot of the basic ones are. And of course, if you're using certificates and have come up with some sort of unique design, you might consider actually working on maybe building your own extension or looking into the process of what that would look like. So at this point, you should be really bored because all I've done is present and read off of a bunch of slides of text, which is why we're going to get maybe a little more interesting, which is to say, maybe you have a certificate on your machine and you've really struggled to figure out what type of certificate is. And even like, okay, I know that this is an actual public key, but can you actually show me the data that's in it? And so typically, most computers these days will have the OpenSSL command line tool on it. And there's a command like this one, which basically says, hey, OpenSSL, I'd like to use the command x509. The man page describes all of the commands that are available. In this case, I know that the input, which is the next flag, is going to be this certificate. And I'd like you to dump out some specific data about it so that I can read it. So we're going to break through this down even further. And saying that the first thing that went wrong with this command is OpenSSL is not always OpenSSL. So OpenSSL is a library of C code, but there are different implementations of it. So for example, if you're on the latest version of Mac OS, you'll note that your version of OpenSSL is actually LibreSSL, which is its own complete unique implementation. Now, for the most part, it's completely compliant with OpenSSL, but of course there are two different code bases, so that's just something to be aware of. Similarly, if you actually go build a Docker container with Ubuntu 18.04 and you go to install OpenSSL, you might see that OpenSSL 1.1.1 gets installed, but that doesn't necessarily tell you what revision of OpenSSL you're actually using. And in order to do that, you actually need to go look at the code base that your distribution is using to compile OpenSSL and take a look at things like that, because as you can see from this output, there's actually nowhere in here that references the fact that this is OpenSSL 1.1.d revision. And so keeping track of what version is actually installed on your machine, especially in production, can be somewhat tricky. And you certainly need to be up to date on those packages if you care about what version is actually running on your host. So back to our command, now that we've realized that OpenSSL is meaningless. So this is a command. And at first, when I first started using OpenSSL, most of these incantations of the CLI were very confusing and tricky. And I just basically copy pasted them off of the internet into my machine and said, oh boy, I hope this works. A few years later, figured out, oh, man pages, those are really helpful. So if you're ever in the issue of like, I don't know what this does, the good news is that most OpenSSL CLIs certainly have decent man pages or the ability to even just ask for help. So here we're using the X509 command because I know that the input for this command, which is this root CA PEM, is an actual X509 certificate. We'll see a little later on where I know that the certificate is a RSA private key. And in that case, we need to tell OpenSSL, hey, the format of that key isn't actually X509, it's RSA. So in order to get the data out of it, we need to specify the right command. And then next, now that OpenSSL has a cert in it, we need to tell it what we're looking for. So in this case, there are some command flags that we provide. Text basically tells it, hey, I'm a human, and I'd love you to put this out in regular text I can read. And no out says, I know that you're typically used to vomit out the normal machine encoded version of the certificate, but I'm a human, and I really don't care about those bits. So back to kind of all the vocabulary we established earlier, we're going to walk through this certificate output. So here we see that OpenSSL did indeed parse the certificate. It's a certificate and it has some data in it. The first piece of data in it is that version. So we see that this certificate is using X509 version 3. The next piece is the serial number. So this is a colon delimited hexadecimal value. And this is actually just a giant large number. That's all it is. Next up is the signature algorithm. So this tells us a little bit about how this certificate and its private key are going to be used together to do encryption bits. So the SHA-256 portion of this tells us that any kind of integrity bits that have to do with how we use this are going to be using SHA-256. And then the actual encryption algorithms used when we encrypt data with this will be of the RSA variety. The next bit is the issuer. So here we can see that there is an organization claiming to be mkcert development CA. There happens to be an organizational unit, which is Alan Sugar at my localhost name. And then there happens to be a common name, which often you'll see is a domain name. So if you're making a cert for example.com, you might see your common name be example.com. But in this case, this certificate in particular is used for signing and creating more certificates. So the CN doesn't necessarily need to be anything special. And here we'll see the mkcert tool just inserts random text, which says, hey, this cert's common name is for Alan Sugar. Finally, we'll see the validity. So we'll note that this certificate is valid not before February 18th at some time, and certainly not after February 18th, 10 years in the future. And so this is important because we could create certificates that need to be used in the future, but we might want to prevent them from being used now. And similarly, we'll create certs now, and we want them to eventually, expire, because we want to ensure that should this key have ever been compromised in any way, that we're always rotating our keys eventually so that we can ensure that they're still secure. Finally, we get to the subject. So in this case, it's a self-signed cert. So all of this data is going to be the same. But for example, if we were to go diagnose another certificate that maybe we were using in one of our service meshes, or we'll see in the future, I believe, maybe not, the subject will eventually be the person who it is who's using this certificate. So this might be the service name of who's using it. Again, we get back into this public key info section. So in order to do encryption with certificates, we need to present people with our public key information. And if you actually look into it, this public key algorithm for RSA is pretty simple. All it tells us is our public key is a certain bit length. The modulus of that key, which is a fancy word of saying a very, very large number. And an exponent, which again is used in the algorithm for doing the encryption. Next up, we'll see that we have extensions. So these were already preconceived extensions that they decided to put into the certificate definition to kind of justify why we might want to build extensions and what their value might be. So here is the key usage of this certificate. So this is a way of saying, certs might have many use cases, but I want to make sure that this cert can only be used for a specific use case. So in this case, it's a certificate to sign, which means this certificate has the capability and should be trusted to sign more certificates versus maybe a key usage of being a web server or a web client. Additionally, we now see basic constraints. So this is typically used to say, if this key can be used for signing, should it be treated as a certificate authority? And if it should be treated as a certificate authority, can it create more certificate authorities or not? And that's what that path length means. So when path length is set to 0, that means from here on out, this key can no longer be used to create more certificates. And there's some more nuance to that path length. I'm not going to cover it in this talk, but it is specified in the RFC. For the most part, you don't have to worry about it until we get to the concept of intermediate certificate authorities. And unfortunately, due to time, that's outside the scope of this talk. So finally, we get to the subject key identifier. So this is an additional way to identify what the ID of this key is. And we'll use that to build a chain of trust here. And we'll start to see how that kind of works. Unfortunately, this talk doesn't go too deep into it. So at this point, there might be questions, and those are great. And I'm just going to reference you to read more documentation. So if you have more questions about, like, how did we come up with this standard? Why is this the standard? What's the bigger historical context for why this exists? I'd strongly encourage you to read this glorious 236-page PDF that kind of explains the fact that most of this technology actually roots itself in the concept that everything should be a directory. And it's kind of funny how the ideas in this paper from 1988 are actually fairly rooted in similar concepts in Consul and this idea of a service registry. You might have also heard me say the word certificate authority, and all of that is basically a fancy way of saying that it's an entity that issues digital certificates. So this is a thing that is capable of creating passports or driver IDs, things like that. In this case, it's a certificate authority is able to create more certificates that could be used to sign more certificates, or leaf certificates that are actually used in our services and at the endpoints of where we're actually using mTLS. So from here, you might have also heard me talk about this chain of trust. And all of this idea is that it's kind of a waterfall down. My brain thinks of it kind of in the reverse order of what this image shows, but this was on Wikipedia and it was pretty easy to source. So the idea here is that we have that end entity certificate. So this is the thing that our service is actually using. And it's going to have an issuer's name that references an intermediate certificate. And that intermediate certificate is going to reference an issuer's name of a root certificate. And basically all of these certs basically say, you should trust me as a service because you trust this intermediate guy, and you should trust this intermediate guy because you trust this root guy. And so that's a way of basically saying, because you trust all these things, you can trust me. The other final chapter of me rambling is cryptographic protocols. So a brief refresher of how we got started with all of this is kind of the misnaming of what an actual certificate is, and the fact that typically certificates are prefixed with the idea of this cryptographic protocol, but the protocols actually have nothing to do with how certificates are formatted. But as a refresher, there are RFCs and drafts on how these cryptographic protocols are supposed to work. And for those who are maybe paying attention or not, Back in June 2018, TLS1 is no longer valid if you want PCI DSS certification. And starting in the first half of this year, Apple, Microsoft, and Google are actually end-of-lifing TLS 1.1 and forcing all of your browsers to start using TLS 1.2. So if you still have a bunch of legacy servers that are not accepting or haven't been upgraded to at least support TLS 1.2, there might be an outage headed your way. And now for some hands-on practice. Ideally, this would have actually been hands-on with live demos, but as you'll see, most of the HashiCorp tools, they already have really reasonably great tutorials, so I'm just going to give you links to that. But the first one is with a tool called mkcert. So if, again, maybe this talk has been completely useless for you, but mkcert might make your life easier. Before we get into mkcert, there's some gotchas. So starting with the latest version of Mac, basically TLS certificates have to be at least 248 bits long to be used. And TLS server certificates now must have a validity of 825 days or fewer, or you need to do something tricky, which mkcert does, which is ensure that all of the certificates that get issued aren't issued at the time that you create them, but are backdated before July 1st. They're obviously working on solutions to this using the Acme protocol, but that's all outside the scope of this talk. So you'll want to go to their website and download this little Golang tool called mkcert. If you're on a Mac, you can just do brew install mkcert. Then it's as simple as running mkcert install. And what mkcert install does is it creates that root CA, both the certificate itself and the private key, and it goes and adds that public cert to be a trusted cert on your machine. And the other cool thing is that mkcert works on Windows, Linux, and Mac. So it's really easy to basically install a root cert that will let you generate more certs so that for local development, you can trust things. Of course, that's all with a caveat that you've now introduced a self-signed cert that can create an endless amount of certs for domains, which means if you're worried about your machine getting compromised, you could now be subject to man-in-the-middle attacks because the attacker could use this mkcert cert to attack you. So there's some danger there. Typically, I just delete the certs every day, or basically on login, just delete the cert. And then if I need mkcert, I'll make a new one for every project I do. But that's because I'm a little paranoid. So you'll see that mkcert creates two certs, like I said, the private key and the public certificate. If we go and use the OpenSSL tooling, we can see that the outputs of this private key are, we know it's in RSA format. And it's basically a bunch of integers used to do the math. So that's pretty cool. Similarly, we can take a look at the root cert and we can see that the subject key identifier is this 93EF, and you'll want to remember that. And finally, we'll now use mkcert to actually build ourselves one of those leaf certificates that we can use in our applications. So in this case, it's created a cert called localhost +2.pem. And localhost key.pem. And if we look at that certificate, we can see that it's got a new serial number that's different than the serial number of our CA. And if we look at the issuer, we can see that the issuer is in fact the data from our CA. And if we look at the validity, we'll see that it's been backdated from June 1st, but it's not to be used until, or it will expire in 2030. And similarly, we'll see that the subject is indeed this development certificate. And we'll see that this certificate should be allowed to be used for web server authentication. We'll see that it's not a CA under those basic constraints. And we should see that the key ID is the authority of this key is 93EF. So that's how we're building that chain of trust, right? Because here I say, hey, you should trust me because of this authority key, because you trust this authority key. And then we'll see that we have these subject alternative names. So because this is a web server, we'll see that these DNS and IP addresses are valid for if I'm connecting to something using this cert, my client should only trust it if I'm coming to it at one of these addresses or this DNS entry. So if we create an Nginx configuration, we should see that we'll use these certs. and we'll go run it with Docker. And we should see that when we go to localhost on Docker that you can actually trust the fact that this cert works. And you didn't have to do any work to manage your trust stores or your keychains on Mac to actually get this to work. And that's the value of mkcert, is that it makes it really simple. I can see that I'm running out of time, so I'm going to start speeding this up. CFSSL is another really great tool. If you want to learn more about Consul, this is a link that will get you to their awesome tutorial about spinning up Consul with mTLS. They actually, in the newer versions of the Consul CLI, have a TLS command for building all these certificates, which is great. They also have an auto encrypt feature that works with their Connect API for setting up your agents to automatically start using certificates within themselves. And the Consul Connect API has an automated CA rotation process. I was currently unable to get that to work on my Mac. I'm certain that it's 90% my problem. And as soon as I find out the issues, I'll submit PRs back to their documentation so that their docs actually work fairly easily. And then I'll as well add a more in-depth tutorial of actually using their documentation so that you'll be able to actually see exactly how this is working in the near future. For Vault, there's been plenty of talks today and probably at least another one in the future. But if you haven't played around with Vault and seen how cool it is, their tutorial is one of the best tutorials on the web to do it. And honestly, if we could build more tutorials that are like the HashiCorp tutorials, the world might be a better place. Nomad is awesome. Nomad has a very pretty great mTLS implementation, and we'll actually get to see some of that soon. And they also use the CFSSL tool to build all of their certificates. And that CFSS tool is a lot more complex than mkcert, which means we can use it to do a lot more interesting things. And it's still a little bit easier to use than the actual OpenSSL tool itself. And future tutorials that I'll write will show off why you might want to use CFSSL instead of just the OpenSSL tooling. So now we'll quickly look over some code, which is unfair because we only have a few more minutes. But basically, when you go to use Consul, you can instruct that all the servers should contain a certificate valid for server.datacenter.domain. And so that's interesting because that means there's got to be code in our Consul agent that's able to actually force the fact that when we're using encryption with Consul, that this contract is true, right? So we would expect that server.datacenter.domain to be in the subject alternative names for our certificates. But what's more interesting is how do they actually enforce that in code? And they do that with a fairly clever wrapper around how the TLS client within Consul gets used, which is to say that when the agent goes to connect to a server, we hijack that TLS client to basically force the fact that the server name for the TLS authentication bit is actually right here verified server.dc.domain. So if you misconfigure your data center or your domain and you go to connect to a bad or like the wrong Consul cluster, your configuration will determine whether or not your Consul agent will actually be able to connect to the cluster. And it's fairly cool how they've wrapped this. And it's definitely an interesting little Golang paradigm. If you've started using Go and want to learn more about how to do some clever wrapping, this is a clever way to go look at that. And then with Nomad, so this addresses the recent CVE. Nomad also uses domain names to basically say whether or not your what role and what region your server should be in. And Nomad actually does this on the TLS server side to do client authentication bits. So if a client comes to Nomad and is an actual client of it, then it should only have client privileges. But if it comes to the cluster as a server, well, then it should be treated as a server. And it does this by using this inside the TLS package of Golang. There's this concept that your TLS client can have a function added to it called verify peer certificate. So this allows you to write any kind of functionality you want around verifying that a peer certificate that you receive back from the client that's connected to you could actually be verified. And it's on you to actually write that logic. And that's exactly what Nomad does. So when Nomad boots up, it gets a TLS config. And we actually set up the incoming TLS configurations to use this function called RPC name region validator. And we'll see that this region validator calls another function called validate RPC region peer. And inside here is where the logic is that actually enforces the fact that if you come into me claiming to be a client, then your name better be client region Nomad. And if you're a server, then you should be allowed to connect. And that's it. I know this talk went by really quick, and I certainly went over time, so I'm glad I had extra time. Right now, this workshop online is garbage, but that should be corrected fairly soon. Building these slides took a lot longer than I thought, so it's unfortunate that those slides haven't been translated here, but this is the link to where I'll be doing all my future work.